For decades, software engineering has been managed around a specific failure, the null point exception. It occurs when a program is running, expecting a piece of data, and instead finds nothing. That missing node causes the entire application to crash. In languages like Java, the responsibility for preventing these crashes falls on the developer. You have to predict every location where a value might be missing and write manual checks to handle it. If a single check is missed, the program fails during execution. Kotlin addresses this by moving the concept of missing data out of the runtime environment and into the static type system. A static type system is a set of rules evaluated by the compiler before the program runs. This split-screen timeline compares the two. On the left, traditional runtime handling results in unpredictable error spikes. On the right, Kotlin's approach builds a gated barrier at the start of the development process. The compiler now enforces these rules as a mandatory part of the build process. If a potential null state is not explicitly handled in the code, the compiler will refuse to generate an executable program. Moving these checks to the compiler forces every developer to address nullability at the moment of declaration. In a large codebase, this structural requirement identifies potential failures that a human reviewer might overlook during a manual check. The foundation of this system is a single rule. By default, all variables are non-nullable. If you declare a variable as a string, it is required to contain actual text data. Assigning a null to a standard string physically rejects the packet, triggering a compilation error. Appending a question mark explicitly declares it nullable, opening a secondary compartment. The compiler now permits the null packet, marked by a green checkmark, while mandating additional safety checks. Requiring developers to label the potential for missing data at the variable level removes ambiguity. The system tracks exactly which references are safe and which require validation, preventing a null value from moving through the program's logic unnoticed. Marking a variable as nullable creates a restriction. Because the compiler knows the data might be missing, it blocks you from accessing the variable's properties using standard methods. Accessing a nullable string's length with standard dot notation hits a compiler barricade. Replacing it with the safe call operator, period dot, converts this into a branching gate. If a null arrives, the operator short-circuits, bypassing the method entirely and routing to a terminal that returns null. This prevents the application from attempting to perform an operation on missing data. Instead of a crash, the safe call ensures the operation results in a null, which is then passed safely to the next step. This short-circuiting behavior acts as a structural guardrail, ensuring an operation on a missing value results in a predictable output rather than program termination. Simply returning a null is only a partial solution. Many functions require a concrete value, such as a specific number or string, to continue their logic. Kotlin uses the Elvis operator logic gate, a question mark and colon, as a sorting node. Valid data passes directly through to the output. If a null hits, the primary path physically blocks, forcing data through a secondary pathway that injects a default value into the output. Using inline routing for default values removes the need for multiple if-else statements. The data pipeline remains linear, as missing values are converted into usable defaults without breaking the flow. In some cases, you need to execute a series of operations that should only occur if a specific piece of data is present. The let function allows you to group these operations into a block. When combined with a safe call, the block only executes if the variable is not null. Inside this block, the verified data is assigned to a temporary reference called it. This process relies on smartcasts, the compiler's flow analysis engine. The compiler tracks the logic of your code and remembers when you have performed a successful null check. This control flow graph shows the checkpoint. When a variable passes through a manual null check, the compiler updates its internal state. As it passes, its visual state lock engages and upgrades color, signifying its permanent reclassification to non-nullable for the remainder of that branch. Smartcasts align the compiler's strict rules with the developer's logic. Once a value is verified, the system removes the requirement for additional checks, keeping the code concise while maintaining safety. There are rare scenarios where a developer knows a variable contains data, but the compiler's static analysis cannot prove it. To handle these cases, Kotlin's not null assertion deliberately overrides safety checks. By using 2 exclamation marks, you command the compiler to bypass all built-in guardrails. If incorrect, a null passes through the hazard-colored till-tilt gate and triggers a catastrophic visual fracture in the flow path. Using the not null assertion reintroduces the exact vulnerabilities found in older languages. Because it bypasses the type system's protection, it is used only as an architectural exception. The toolkit, from non-nullable types to safe calls and default routers, functions as an integrated logic chain. Each piece relies on the same underlying type system to maintain safety across the application. A potential issue is creating excessively long logic chains. This tangled wire represents how multiple safe calls become difficult to read. Best practice involves breaking these chains into separate manageable assignments. This maintains clarity while keeping safety intact. Kotlin's architecture is built on the principle that the compiler should validate data states before the program is ever deployed. Missing data is an inherent part of software development. By shifting the handling of this data from runtime guesswork to the strict rules of the compiler, Kotlin provides a framework to manage nullability as a predictable part of the system's design.